For grounding equipment, specifically motors and instruments within the skids, the ground can be carried out to the skids by way of a ground bus in the main control panel. The ground wire from the main control panel should connect to the ground bus in the skid, and the equipment within the skid should be grounded to the ground bus. For non-current carrying equipment like vessels, tanks, and machine frames, the ground from the main control panel can be used for grounding non-current carrying equipment mounted on concrete pads. The ground wire from the main control panel should connect to a grounding electrode system installed in the concrete pad. The grounding electrode system, or GES, for the main control panel should be installed in accordance with Section 250.52 of the National Electrical Code. The GES should consist of one or more of the following: firstly, a metal underground water pipe; secondly, a metal frame of the building; and thirdly, a ground rod driven into the earth. The ground wire from the main control panel should be connected to the GES. A separate building ground is not required for the equipment in this case, as the ground from the main control panel can be used for both the equipment and the non-current carrying equipment. However, if the building has a separate grounding electrode system, it is acceptable to connect the ground wire from the main control panel to both the building GES and the GES for the main control panel. Additional considerations include grounding conductor size. The grounding conductor from the main control panel to the GES should be sized in accordance with Table 250.122 of the NEC. Ensure that there is a continuous path for ground current from all equipment and non-current carrying equipment back to the GES. The resistance of the GES should be as low as possible to ensure effective grounding. Let's delve deeper into the specifics of grounding, especially when dealing with a 480 volts main control panel serving modular skids. Grounding, at its core, is about providing a safe path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault. This protects personnel and equipment from dangerous voltage levels. When you have a 480 volts main control panel, or MCP, feeding modular skids, the grounding approach must adhere to the National Electrical Code, specifically Article 250. The primary question is whether you can extend the ground from the MCP to the skids for grounding the motors and instruments, or if a separate building ground is required. The answer, according to the NEC, is that you can indeed extend the ground from the MCP to the skids. This is achieved by establishing a solid grounding electrode system at the MCP and then running an equipment grounding conductor, or EG, from the MCP to each skid. Within each skid, the EGC should terminate on a ground bus or a designated grounding point. All equipment within the skid, including motors, instruments operating at both 110 volts alternating current and 24 volts direct current, and other electrical components, should then be bonded to this ground bus. This creates a common ground reference within the skid and provides a lower impedance path for fault current. The size of the equipment grounding conductor running from the MCP to each skid is crucial. It must be sized according to NEC Table 250.122, which bases the EGC size on the rating of the overcurrent protective device protecting the circuit feeding the skid. In this case, the circuit is rated for 200 amps, so you would need to consult Table 250.122 to determine the appropriate size for the EGC. It's imperative to use a copper conductor of the correct gauge or an aluminum conductor with the appropriate adjustments for ampacity and termination. Now, let's address the grounding of non-current carrying equipment, such as vessels, tanks, and machine frames mounted on concrete pads. These items are not directly part of the electrical circuit but can become energized under fault conditions. The NEC requires that these items also be grounded to minimize the risk of electric shock. The ground from the MCP can be used for grounding these non-current carrying items. The best practice is to extend the EGC from the MCP to a grounding electrode system installed in the concrete pad. This could involve driving ground rods into the earth near the pad and connecting them to a ground bus or a grounding plate embedded in the concrete. The non-current carrying equipment should then be bonded to this grounding point. It is important to remember that the grounding electrode system at the concrete pad should be bonded back to the main grounding electrode system at the MCP. This ensures that all grounding points are at the same potential. This bonding conductor should also be sized according to NEC Table 250.66, which bases the size on the size of the largest ungrounded conductor feeding the MCP. Regarding the grounding electrode system for the MCP itself, Section 250.52 of the NEC specifies acceptable grounding electrodes. These include, firstly, a metal underground water pipe that is in direct contact with the earth for at least 10 feet. Secondly, the metal frame of the building if it is effectively grounded. Thirdly, a ground rod or pipe driven into the earth. Fourthly, a ground ring encircling the building. And fifthly, other types of electrodes as permitted by the NEC. The choice of grounding electrode will depend on site conditions and the availability of suitable electrodes. The NEC requires that the grounding electrode system have a resistance to ground of 25 ohms or less. If a single ground rod does not achieve this resistance, a second ground rod must be installed at least 6 feet away from the first. In some cases, it may be necessary to use multiple ground rods or other types of electrodes to achieve the required resistance. The grounding conductor connecting the MCP to the grounding electrode system must be sized according to NEC Table 250.66, as mentioned earlier. This conductor must be securely connected to both the MCP and the grounding electrode. Now let's clarify the need for a separate building ground. The NEC generally allows for the use of a single grounding electrode system for a building, and in your case, the grounding electrode system at the MCP can serve as the primary grounding electrode system for the skids and associated equipment. However, if the building has its own separate grounding electrode system, it is permissible to connect the ground wire from the MCP to both the building GES and the GES for the MCP. This creates a redundant grounding system and can further enhance safety. However, it is crucial to ensure that the two grounding electrode systems are properly bonded together to avoid any potential differences in ground potential. Finally, let's emphasize the importance of equipment grounding continuity. This means that there must be a continuous, low impedance path for ground current from all equipment and non-current carrying equipment back to the GES. This is typically achieved by using properly sized and installed equipment grounding conductors. All connections must be tight and corrosion-free to ensure good electrical contact. Regular inspections and testing of the grounding system are essential to verify its effectiveness. This includes visual inspections of grounding conductors and connections, as well as testing the resistance of the grounding electrode system. Any deficiencies should be promptly corrected to maintain a safe and reliable electrical system. In summary, grounding a 480 volts main control panel serving modular skids requires careful attention to detail and adherence to the NEC. By establishing a solid grounding electrode system, running properly sized equipment grounding conductors, and ensuring grounding continuity, you can create a safe and reliable electrical system that protects personnel and equipment from electrical hazards. Remember to consult the latest edition of the NEC and consult with a qualified electrical engineer or contractor for specific guidance on your application. Now let's talk about some key considerations when implementing a grounding system for a 480 volts main control panel, or MCP, that feeds modular skids containing motors, instruments, and other electrical equipment. Firstly, understanding the role of grounding is paramount. Grounding is not just about connecting to the earth, it's about creating a low impedance path for fault current to return to the source, enabling overcurrent protection devices, such as circuit breakers and fuses, to quickly and safely clear the fault. This protects personnel from electric shock and prevents damage to equipment. The National Electrical Code, or NEC, specifically Article 250, provides detailed requirements for grounding and bonding electrical systems. Secondly, let's consider the main control panel's grounding electrode system. The MCP should have a robust grounding electrode system that meets the requirements of NEC Section 250.52. Acceptable grounding electrodes include, firstly, a metal underground water pipe in direct contact with the earth for at least 10 feet. Secondly, the metal frame of the building if it is effectively grounded. Thirdly, a ground rod or pipe driven into the earth to a depth of at least 8 feet. Fourthly, a ground ring encircling the building. And fifthly, other listed electrodes. The grounding electrode system should have a resistance to ground of 25 ohms or less. If a single ground rod does not achieve this resistance, a supplemental electrode, such as a second ground rod, is required. The grounding electrode conductor, which connects the MCP to the grounding electrode system, must be sized according to NEC Table 250.66. Thirdly, let's discuss equipment grounding conductors, or EGs. The EGC is the path that provides a lower impedance fault current path from the equipment back to the source. In this case, the EGC runs from the MCP to each skid and then to each piece of equipment within the skid. The EGC can be a wire, a conduit, or other approved raceway. The size of the EGC must be based on the rating of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. For a 200 amp circuit, you would need to consult Table 250.122 to determine the appropriate size for the EGC. It is crucial to use the correct size EGC to ensure that it can safely carry the fault current. Fourthly, consider bonding. Bonding is the process of connecting all non-current carrying metal parts of the electrical system together to create a common ground potential. This includes equipment enclosures, metal conduit, and other metal structures. Bonding helps to minimize voltage differences between these metal parts, reducing the risk of electric shock. All bonding connections must be tight and corrosion resistant. Fifthly, grounding of non-current carrying equipment. Non-current carrying metal parts, such as vessels, tanks, and machine frames, must also be grounded. This can be achieved by connecting them to the equipment grounding conductor system. If the equipment is mounted on a concrete pad, a grounding electrode system should be installed in the pad and connected to the equipment. The grounding electrode system in the pad should be bonded back to the main grounding electrode system at the MCP. Sixthly, separate building grounds. While a separate building ground is not typically required, it is permissible to connect the MCP grounding system to the building grounding system. This can provide additional redundancy and improve overall grounding performance. However, it is important to ensure that the two grounding systems are properly bonded together to avoid any potential differences in ground potential. Seventhly, grounding for sensitive equipment. Sensitive electronic equipment such as PLC and instruments may require special grounding considerations. It is important to follow the manufacturer's recommendations for grounding this type of equipment. In some cases, it may be necessary to provide a separate, isolated ground for sensitive equipment to minimize noise and interference. Eighthly, grounding in hazardous locations. If the skids are located in a hazardous location, such as an area with flammable gases or vapors, additional grounding requirements may apply. The NEC provides specific requirements for grounding in hazardous locations in Article 500 through 516. Ninthly, inspection and testing. After the grounding system is installed, it is important to inspect and test it to ensure that it meets the requirements of the NEC. This includes visual inspections of all grounding connections and testing the resistance of the grounding electrode system. Regular inspections and testing should be performed to maintain the integrity of the grounding system. Tenthly, documentation. It is important to maintain accurate documentation of the grounding system, including drawings, specifications, and test results. This documentation can be helpful for troubleshooting and maintenance purposes. Finally, remember that grounding is a critical aspect of electrical safety. It is important to consult with a qualified electrical engineer or contractor to ensure that the grounding system is properly designed and installed. The NEC is a complex document, and it is essential to have a thorough understanding of its requirements to ensure a safe and reliable electrical system. By following these considerations and adhering to the NEC, you can create a robust and effective grounding system for your 480 volts main control panel and associated skids. This will help to protect personnel from electric shock, prevent damage to equipment, and ensure the safe and reliable operation of your electrical system. Grounding is a fundamental aspect of electrical safety, and it is crucial to get it right.